So now we need to think about what's happening in terms of the energy of a system, of an oscillating system. Now, this could be for a pendulum or for a mass spring system. And remembering that we're starting at maximum displacement, we need to think what's happening to the energy. Well, at maximum displacement, imagine that we are holding the pendulum here, about to let it go. The energy that it's got there is potential energy, gravitational potential energy. As it swings towards the equilibrium position, that gravitational potential energy is going to change to kinetic energy. Until when it gets to the bottom of the swing, it's going to have minimum gravitational potential energy and maximum kinetic energy. So at the bottom, it's kinetic energy. So at the equilibrium position, its kinetic energy is going to be maximum. This means that the entire energy in the system, the total energy, is equal to either the maximum kinetic energy or the maximum potential energy. Here I've got a graph. You can see that at maximum displacement we have maximum energy, so we know that this is going to be the graph for potential energy. As the pendulum swings towards the equilibrium position, that gravitational potential energy is going to be changed into kinetic energy. And so if we drew a graph of kinetic energy, it starts at 0 at the amplitude or maximum displacement and increases corresponding to the loss in potential energy. So the total energy of my system is equal to either the maximum kinetic energy or the maximum potential energy. And you need to be familiar with this graph. Starting at maximum displacement, the one that starts at the top is our potential, the one that starts with no energy at maximum displacement is our kinetic. So if we look at that graph again, we know that the total energy is equal to the maximum kinetic energy. So the kinetic energy at the equilibrium position, where x equals 0, is going to be our maximum. That's our total energy. So we know for a spring that the potential energy stored in it is equal to 1/2 times the spring constant, and that's our k, times the displacement squared. And we also know that the total energy in the system is equal to the maximum potential energy. So therefore we substitute our A in for our x, and we get that the total energy in the system is equal to 1/2 k times the amplitude squared. But we also know that the total energy in the system is equal, for any particular displacement, not just at the amplitude, to the sum of the kinetic and potential energies. So we can rearrange that equation to get a form for the kinetic energy at any displacement x. It's just going to be the total energy minus the potential energy. Now the potential energy we were given up here, and we know that the total energy is equal to 1/2 k a squared. So the kinetic energy at any displacement x is equal to 1/2 k a squared minus 1/2 k x squared. And we can separate that out into brackets to give us the kinetic energy equation for any particular displacement. This is Ke at a particular displacement x. 1/2 k brackets a squared minus x squared, where a is our amplitude and x is the displacement at any point. Now taking that equation, we can then get the speed equation for an oscillating system, or for a mass spring system in particular, but for any oscillating system really. Half k a squared minus x is our kinetic energy, but kinetic energy is a half mv squared. So, knowing that 2 pi f squared is equal to k over m, because that's our SHM constant that we've looked at a few times, and knowing that when we rearrange this to get v squared, we will get that v squared is equal to a half k a squared minus x squared over m, and that half will become a 2 on the top. Well, those two are going to cancel, and k over m is here. So we can substitute 2 pi f squared in for that k over m factor, and we end up getting that the velocity squared of our mass on the end of a spring, that's our equilibrium position at any displacement x, is going to be equal to 2 pi f squared times the amplitude squared minus that x, that displacement squared. As a result, we can just root everything to get an equation for the velocity. The velocity of my oscillating mass at a particular displacement from the equilibrium position x is equal to plus or minus 2 pi f root a squared minus x squared. Why plus or minus? Well, it depends on whether it's to the left or the right of my equilibrium position.